Physicists have for some time been captivated by dark openings, a peculiarity that has charmed researchers for more than a century. These monstrous elements, which oppose how we might interpret gravity, remain largely imperceptible to us. A black hole with a mass that could be 2 to 4 million times that of the Sun is extraordinarily strong. Yet, due to the research conducted over the course of recent decades, we've progressed from knowing practically nothing about them to uncovering an ever-increasing number, sometimes in astounding ways. As of late, an advancement has happened. Specialists, including those at the Kaku Foundation, reported that they've figured out how to look inside a black hole. This new information has illuminated features of the universe that science might have neglected in the past. We should dive into black holes and discover what exists in space is tremendous and inspiring. Yet, before diving into what was uncovered in recent discoveries, it's critical to understand the basics of what black holes are. Many people are aware of black holes, but there are still significant gaps in how we might interpret them. The concept of a black hole became theoretically possible in 1916 when Albert Einstein published his general theory of relativity, which predicted the presence of such objects. However, black holes remained simply speculative until the 1960s when researchers first noticed undeniable proof supporting their existence. While studying the binary star system Cygnus X1, cosmologists identified an unusually dazzling blue star emitting X-rays. This star was certainly not a normal heavenly body. It was orbiting a strange, massive object. After further assessment, it was clear the X-rays were not just floating around in space but were being pulled toward the dark substance, confirming the presence of black holes. This was a momentous discovery showing that black holes were not just hypothetical constructs, but real phenomena. The significance of this revelation couldn't be more important. It meant that a completely new class of objects existed in space, requiring urgent and thorough study. Researchers from around the world directed their focus toward black holes with renewed attention. The first identified black hole, Cygnus X1, is situated around 6,000 light-years from Earth in the Cygnus constellation. It is commonly brighter than our Sun and has an enormous gravitational pull, so strong that not even light can escape it. For this reason it's called a black hole. The concept of a black hole is both captivating and terrifying. It refers to a region in space where the gravitational force is so intense that nothing, not even light, can escape its pull. Anything that gets too close to a black hole is irresistibly drawn in, doomed to be lost forever. This danger makes the study of black holes both fascinating and essential. However, are we in any imminent danger from them? Despite the nearest black hole being around 500 light-years away, this distance still raises questions about potential dangers. Still, the true extent of black holes is still emerging. After the discovery of Cygnus X1, astronomers began searching for other black holes. It's now believed that there may be upwards of 100 million black holes in our Milky Way galaxy alone, but identifying them remains a considerable challenge. Estimates suggest that many of them exist within our galaxy, highlighting the importance of studying these enigmatic objects. The primary concern with black holes is their enormous gravitational force. This pull is so strong that it pulls everything, even light, into itself. The center of the black hole, known as the singularity, is where all the matter that falls into it is compressed into an incredibly dense point. In simpler terms, black holes act as cosmic vacuum cleaners, sucking everything in their vicinity. If someone were to fall into a black hole, they would be progressively stretched and compressed until they were reduced to a singularity. This process is incredibly slow, meaning the person would meet their end long before the final irreversible stage. Yet, despite the obvious danger, black holes are so widespread that they can't be ignored. Even though the closest one is far away, their sheer number within our universe makes them a critical subject of scientific study. In 2019, researchers achieved a historic feat by capturing the very first clear image of a black hole, the massive black hole at the center of the M87 galaxy. This photo was obtained over several nights, and with each exposure, new insights were gathered. The data was then carefully organized to reveal a clearer image. The most striking discovery was that a black hole isn't a singular void in space. It consists of 3 distinct layers. The first layer is known as the event horizon, which marks the point beyond which nothing can return. Once an object crosses this boundary, it is inevitably drawn toward the black hole. The second layer is the photon sphere, where light is caught in orbit. Any light that enters this region is trapped in the black hole's gravitational grasp and cannot escape. Finally, the third layer is the singularity, where matter is crushed down to a single point in spacetime, creating an environment where the laws of physics as we know them cease to function. This breakdown of the laws of physics is one of the many reasons studying black holes is so difficult and captivating. What's even more fascinating is that each black hole behaves differently. While they tend to have the same basic structure, the way each one operates can vary. Unlike other objects in the universe that we can study directly, black holes must be examined indirectly. Scientists use observations of the radiation emitted by black holes and the gas and dust surrounding them. It's difficult to send a probe into a black hole because, once an object crosses the event horizon, there's no way for it to escape. This makes direct exploration of black holes impossible. Instead, researchers must rely on indirect observations and mathematical models to infer the properties and behavior of these mysterious objects. The study of black holes also raises profound questions about the nature of the universe itself. For example, what happens to information that falls into a black hole? This is known as the black hole information paradox. According to quantum mechanics, information cannot be destroyed, but classical physics suggests that anything that enters a black hole is lost forever. Resolving this paradox is one of the biggest challenges in modern physics and could provide us with a deeper understanding of the fundamental laws governing the universe. Another fascinating aspect of black holes is their role in galaxy formation and evolution. It's now believed that most, if not all, large galaxies, including our own Milky Way, harbor supermassive black holes at their centers. These black holes may have played a crucial role in shaping the galaxies we see today, influencing their growth and development over cosmic time. Despite the many unknowns surrounding black holes, the breakthroughs in black hole research over the past few decades have been nothing short of extraordinary. From capturing the first image of a black hole to unraveling their complex internal structure, scientists are steadily peeling back the layers of mystery surrounding these enigmatic objects. As technology advances and our understanding of physics deepens, it's likely that we will continue to uncover new and surprising insights into the nature of black holes and their place in the cosmos. In the end, the study of black holes not only challenges our current understanding of the universe but also inspires new avenues of research. It forces us to reconsider our assumptions about space, time, and the very fabric of reality. The exploration of black holes is, without a doubt, one of the most exciting frontiers in modern science, offering the potential to revolutionize our understanding of the universe in ways we can only begin to imagine. Anything that crosses the occasion skyline is maneuvered into the peculiarity, where it would be squashed to an imperceptibly little point. This presents a huge impediment for researchers without the capacity to concentrate on dark openings in the conventional manner. Specialists are compelled to work with two-dimensional models to comprehend these three-dimensional objects. Moreover, dark openings come in various shapes and sizes, making it considerably more testing to concentrate on them. Researchers have fostered a few hypotheses to make sense of how they form, with one of the most unmistakable being that dark openings start from falling stars. When a star runs out of fuel, it can never again produce the energy expected to balance the force of gravity, making it collapse. In the event that the star is gigantic enough, this breakdown goes on until the star turns into a peculiarity. NASA specialists have zeroed in on an especially strong galaxy, M87, where they noticed a tremendous whirlpool of hydrogen gas pivoting at a surprising rate of 1.2 million miles per hour. Regardless of the enormous powers at play, the gas didn't fly separated, leading researchers to reason that there must be a huge object at the focal point of the system maintaining a level of control. This object ended up being a dark opening, gauging billions of times the mass of the Sun. In 1963, New Zealand mathematician Roy Kerr utilized Einstein's conditions to give a model for turning dark openings. Kerr's hypothesis suggested that, as opposed to imploding into a particular point, a turning dark opening could frame a ring of fire or a growth plate. This circle would pivot so quickly that the outward forces would neutralize the gravitational breakdown. Kerr's work likewise presented the idea of the Einstein-Rosen bridge or wormhole. A wormhole is a theoretical passage that interfaces two far-off focuses in space-time, potentially in any event, connecting parallel universes. The idea of wormholes has entranced researchers for a really long time. If dark openings are to be indeed associated with wormholes, they could offer an easy route through space-time, permitting travel between far-off locales of the universe or even between various times. Anyway, regardless of whether wormholes exist, it's impossible that we would have the option to go through them at any point in the near future. As per Einstein's hypothesis of extraordinary relativity, the speed of light is a definitive cutoff for how quick anything can travel, and this presents an obstruction for involving wormholes for faster-than-light travel. By the by, wormholes keep on being an enthralling subject of hypothetical exploration. If they were solved, they could give a method for bridging tremendous distances of space, or even to various times. A few physicists likewise suggest that wormholes could offer a mechanism for time travel. Anyway, the difficulties of crossing a wormhole are colossal, as they would probably be unsteady and encircled by outrageous radiation and gravitational forces. To genuinely comprehend the idea of dark openings, physicists should foster a brought-together hypothesis that consolidates both Einstein's hypothesis of general relativity and quantum mechanics. One promising contender for this hypothesis is superstring theory, which suggests that the central particles of nature are truly small vibrating strings. These strings could make sense of a significant number of the baffling peculiarities known to man, including the formation of dark openings and wormholes. Superstring theory additionally suggests that dark openings, wormholes, and other colorful answers to Einstein's situations might emerge because of the bowing of spacetime by these small strings. In spite of its contribution, superstring theory requires the presence of extra dimensions of spacetime that are excessively little for us to recognize. Anyway, exploration into dark openings and their secrets keeps on pushing the limits of our comprehension. Perhaps one of the most historic thoughts connected with dark openings is the idea of Hawking radiation, proposed by physicist Stephen Hawking in 1974. This hypothesis suggests that dark openings are not totally dark, but transmit faint radiation because of quantum impacts close to their occasion horizons. This radiation could make the dark opening gradually lose mass over time, ultimately leading to its vanishing. Hawking radiation is hard to distinguish anyway because of its frail nature. Still, this thought offers important insight into the behavior of dark openings and their role in the universe. Dark openings additionally provide an exceptional lab for concentrating on the interaction between gravity and quantum mechanics. The outrageous circumstances close to a dark opening's peculiarity are where both gravitational forces and quantum impacts become possibly the most important factor, making them a critical area of exploration for physicists hoping to foster a hypothesis of quantum gravity. The investigation of dark openings may likewise hold hints to understanding the origins of the universe. A few hypotheses suggest that the circumstances close to a dark opening could offer insights into the introduction of spacetime itself. Furthermore, assuming wormholes really do exist, they could give a mechanism for exploring immense regions of spacetime, offering additional opportunities for interstellar travel. Although these ideas are still speculative, they continue to inspire scientists to explore the most profound questions about the nature of our universe. As researchers delve deeper into the mysteries of dark openings and wormholes, there are still many unanswered questions that challenge our understanding of physics. One of the key puzzles is the information paradox. This paradox arises because, according to traditional physics, anything that falls into a black hole is lost to the universe, including the information about the state of that matter. However, quantum mechanics suggests that information can never be destroyed, which leads to a contradiction when it comes to the behavior of black holes. Stephen Hawking, who initially suggested that information was lost in black holes, later revised his position, proposing that black holes might not completely erase information but could instead encode it in some way that could eventually be recovered. This idea sparked a new wave of debate among physicists about whether black holes might ultimately provide a way to reconcile quantum mechanics with general relativity, two fundamental theories that, until now, have resisted being unified. Another major area of investigation is the role of dark energy and dark matter in the behavior of black holes. These mysterious substances make up most of the universe, but their nature is still not well understood. Dark energy, which seems to be responsible for the accelerated expansion of the universe, could have an impact on the formation and evolution of black holes. Similarly, dark matter might play a role in the gravitational interactions around black holes, affecting their growth and behavior over time. As technology improves, we may soon have more tools at our disposal to study these enigmatic objects. The Event Horizon Telescope, for example, provided the first-ever image of a black hole in the galaxy M87, which was a groundbreaking achievement in the study of black holes. Such observations, combined with new theoretical work, could soon provide clearer insights into the true nature of black holes, wormholes, and the fundamental structure of the universe. While the mysteries surrounding black holes may seem insurmountable, they remain at the cutting edge of scientific exploration. Each new discovery brings us a little closer to understanding the most fundamental questions about space, time, and the universe itself. It is likely that in the future, black holes and the phenomena associated with them will continue to offer profound insights into the laws that govern reality, leading to breakthroughs in both theoretical physics and our understanding of the cosmos. As our knowledge of these cosmic giants expands, we may find that black holes hold the key to unlocking some of the deepest secrets of the universe.